Sound check, sound check. So chemistry, we're moving on to our next lesson, which is the second lesson in the concept of empirical formulae. In this lesson, you're going to learn how to use an empirical formula as an intermediate step to finding the actual molecular formula of a compound. So a hydrocarbon is a compound made of carbon and hydrogen. A combustion reaction burns a hydrocarbon with oxygen and produces carbon dioxide and water. And there are many different types of hydrocarbons that you can use in this type of reaction. It has the general formula CXHX, where the CXHY, where the H and the Y represent some subscript, and that's what we're trying to learn in this particular reaction, this experiment, is how to determine what those subscripts of X and Y are there, and therefore we would be able to identify what hydrocarbon that is. But this is what a combustion reaction looks like. It takes a hydrocarbon, it burns it in oxygen. Basically, you light a match to it and it starts to burn. So it's combustion means to burn. And what it produces, all combustion reactions produce carbon dioxide and water. So let's see how we use empirical formulas to figure out what the subscripts X and Y are for that hydrocarbon. So our goal is to determine the chemical formula of the subscripts for an unknown compound, in this case the hydrocarbon, the CH compound. Okay, so here's the example. Combustion of an unknown hydrocarbon produces 5.72 grams of CO2 and 1.17 grams of H2O. Determine the empirical formula of the compound. Okay, so we're going to first determine the empirical formula, and we have a way to measure how many grams of CO2 and how many grams of water that we get out of this reaction. So once we have those masses in grams, the first step is, in the lab, we burn the unknown hydrocarbon in a combustion reaction and weighed the number of grams of each of the products, CO2 and H2O. Okay, so the analysis is, in the lab, we burned the unknown hydrocarbon in a combustion reaction and weighed the number of grams of each of the products, CO2 and H2O. Okay, so here's our world, and we're able to measure the mass of the output, the products of that reaction. Then we can use our periodic table to come up with the molar mass for each of those compounds. CO2 is 44.01 grams, and H2O is 18.02 grams per mole. So again, our goal is to determine the chemical formula of the subscripts for an unknown compound. So step 2, we convert grams to moles, just as we did in the last lesson. Anytime you're dealing with a chemical compound or a chemical reaction, you have to be in moles. Chemical reactions don't understand weight. They don't understand grams. So we're going to use the molar mass conversion. So for CO2, we have 5.72 grams, and we know that 1 mole is 44.01 grams. So there's mass, there's the molar translator, and there's the moles. So we want the grams of CO2 to cancel out, so that's why we put this conversion factor the way we did, with moles on top and grams on the bottom. So the last man standing is moles of CO2, and that's what we want in our final answer. And so what we have is 0.13 moles of CO2. Now we do the same thing for the water. We have 1.17 grams of water. We use the molar mass for water so that grams of H2O cancels out like that. The last man standing is the moles of H2O, and we get 0.65 moles of H2O. So now we're going to first work to figure out what the subscript for C is, for the carbon. So So step 3, let's look at the flow of what's going to happen here. Now, you're not going to understand this the first time. You're going to want to watch this 2, 3, 4, 5 times before it really totally makes sense, okay? But try to follow it step by step. First of all, we note that there is 1 mole of carbon for every 1 mole of carbon dioxide. So that's 1 carbon dioxide, 1 mole of carbon dioxide. You don't see the 1 out in front, but it's implied to be there. And you see that you need 1 mole of carbon to make 1 mole of carbon dioxide. And all of the carbon in the CO2 molecule or mole must have come from the CXHY compound. Why? Because that's the only carbon there is on the left side of the arrow. So the carbon on the left side of the arrow has to move over and become the carbon on the right side of the arrow, and we need exactly the same number of moles in both of those places, because you can't create or destroy molecules or moles. Whatever you have in the reactants has to be the same in the products. Okay, so here we go. We start off with 5.72 grams of CO2, and now we're going to do the molar mass conversion, and that gets us to the number of moles of CO2. What we just saw, and that's going to be 0.13 moles of CO2. Then we remember, look up there at the equation, that there's 1 mole of carbon for every 1 mole of CO2. You don't normally write those ones, but just so you're clear that they're there, it's a 1-to-1. We have 1 mole of carbon for every 1 mole of CO2. So we're going to write that down below. 1 mole of carbon for every 1 mole of CO2. And so when we do the math on that equation, we get 0.13 moles of carbon. So there we go. So we know that on the product side we have 0.13 moles of carbon. Therefore, all of that carbon had to come from the same place. Therefore, that carbon, 0.13 moles, came from there. And so we can change that subscript X to that number to 0.13. So we figured out how many moles of carbon. Okay, now we're going to move on and we're going to do the moles of hydrogen. So there's the grams of hydrogen. Now we use the molar mass of water, and it's 1 mole of water for every 18.02 grams. And then we look up at the formula for water, and we notice we have to have 2 moles of hydrogen atoms for every 1 mole of H2O. So we have 0.065 moles of H2O, and again we have 2 moles of hydrogen for every 1 mole of H2O. So there you have it down there on the bottom in the equation. 2 moles of hydrogen for every 1 mole of H2O. And when you run the numbers, you get 0.13 moles of H2O. So we can go ahead and put that up here. And that means we must have had 0.13 moles of H2O over here on the left. All of the hydrogen, excuse me, not of H2O, of H. All of the hydrogen on the left side had to become hydrogen on the right side. And you have to end up with the same amount of hydrogen as you had at the beginning. So therefore we can change that subscript to 0.13. So there we have our subscripts. But what do we know about those subscripts? They have to be whole numbers. They have to be integers. So we're going to go ahead and we're just going to place one of them over the other. It doesn't matter which is which. Remember, you always place the smaller one on the bottom, but they're both the same number, so it doesn't matter which one you place on top and bottom, and that gives you a ratio of 1-to-1. Therefore, the empirical formula for this compound is C1H1, or we just write it as CH. So that's how you get the empirical formula. Now, if you need to go back and watch this again, do it. You don't learn things watching them one time. You have to watch things in a subject like chemistry 2, 3, 4, 5 times before they start to make sense. Okay, now the molecular formula of a compound is the actual chemical formula. In the previous problem, we found the empirical formula for a hydrocarbon compound to be CH for that particular hydrocarbon. But there's an infinite possible number of molecular formulas that could have that empirical formula. CH could be the actual molecular formula, or it could be C2H2, C3H3, C4H4, C5H5, and so on. There's an infinite number of possibilities that could have the molecular formula CH. So we need one more piece of information to find out the actual molecular formula. Okay, so how can we know what the actual molecular formula is if we know the empirical formula? The answer is, if we know the molar mass of the compound, we can derive the molecular formula of the compound from the empirical formula. So example, it is determined that the molar mass of this CH compound from the previous problem is 78.11 grams. What is the true molecular formula of the compound? Now I'm just going to ask you to accept that there is a way to know the molar mass of this compound without actually knowing its formula. And we'll talk about that at another time. It's too much information for right now, but there is a way to get the actual molar mass of this compound without knowing its formula. So we're going to show you how you can use the molar mass to figure out its formula. Note, we will leave the question of how the molar mass of an unknown gas is determined for another discussion. Okay, so there we have it again. 78.11 grams is the actual molar mass for this unknown compound. So we compute a scaling factor, which we'll call letter N, based on the ratio of the molar mass of the actual gas, that's the 78.11, over the molar mass of the empirical formula. So we need to figure out what that is. So there's the formula. N equals molar mass of the actual compound, 78.1, over the empirical formula molar mass. So let's go ahead and calculate that. So we determine the molar mass is 78.11 grams. So the empirical molar mass for CH is 1C and 1H. So that's 12.01 grams for carbon, 1.01 grams for hydrogen. So that's 13.02 grams for CH. That's the empirical molar mass. So multiply the subscripts of the empirical formula, that's 1 for C and 1 for H, by the factor N. So here we're going to compute the factor N. There's that formula again, and it's going to be 78.11, the actual molar mass, over the empirical molar mass that we just calculated is 13.02, and that gives you approximately an N factor of 6. So therefore we multiply the subscripts and the empirical formula, that's 1 for carbon and 1 for hydrogen, by 6. And you come up with the molecular formula, that this is the actual molecule that actually exists in the real world, and that's C6H6. So again, there is no molecule CH. Okay, the empirical formula is simply a middle step to get us to the molecular formula of a real compound, in this case C6H6. There is such a compound as C6H6. And so that's how we use empirical formula to determine the molecular formula of an unknown compound. Okay, we're going to do another example. Okay, so combustion of an unknown hydrocarbon produces 33.01 grams of carbon dioxide and 13.51 grams of water. Determine the empirical formula for the compound. So there again is another combustion reaction. Looks exactly like the one in the previous example. Okay, so we're going to start off with the carbon dioxide to try to figure out the carbon, the number of moles of carbon. So we start off with 33.01 grams of CO2. We use the molar mass of CO2, 1 mole of CO2 for 44.01 grams of CO2, and that gives us the number of moles of CO2. So there it is, and that would be 0.75 moles of CO2. Again, we note that there's 1 mole of carbon for every 1 mole of CO2 based on the formula for CO2. So 1 mole of carbon for every 1 mole of CO2. So if you do the calculation, that gives you 0.75 moles of carbon. And all of that carbon could have only come from one place, and that's from over here from our hydrocarbon. That means we started off with 0.75 moles of carbon. So that is going to take the place of X and be our subscript. Okay, do the same thing for hydrogen. Now, you should be trying to do this on your own. Okay, do as many of these steps on your own as you can and find out where you're getting stuck. So here we go. We have 13.51 grams of water. We need to know the molar mass of water to figure out the number of moles of water. So it's 1 mole for every 18.02 grams of water. And that will give us 0.75 moles of H2O. Now, if we look at the formula for water, H2O, we notice that we have 2 moles of hydrogen atoms for every 1 mole of water molecule. So it's a 2-to-1 relationship. So we write that in our formula down below. 2 moles of H for every 1 mole of H2O. And when you do that calculation, you get 1.5 moles of hydrogen. And all of that hydrogen had to come from the hydrocarbon over on the left side. So we're going to go ahead and take that 1.5, bring it there, bring it up there, and that becomes our subscript. Okay, so again, we have to get from these decimal numbers in the subscripts to whole numbers. So that's the next step. So we have 1.5 moles of hydrogen. You put the smaller of the 2 numbers on the bottom. That's the 0.75 moles for carbon. So you have 1.5 over 0.75, which equals 2-to-1. That means you have twice as much hydrogen as carbon. So the empirical formula for this compound is CH2. Okay? Now we're going to go on to find the actual molecular formula for this compound. So let's read this. If in a lab experiment you calculate 1 mole of gas has a mass of 28.06 grams, what is the molecular formula? That is the actual formula for the CH compound. Okay, so we take the molar mass, that's what was given to us of the actual compound, 28.06. And now down on the bottom we needed to calculate the empirical mass. So there's 1 carbon and 2 hydrogens. So its carbon is 12.01, hydrogen is 1.01. You multiply the hydrogens by 2 because there's 2 of them, and you get 14.03 grams of CH2. So there's the formula. Now we plug in the numbers, 28.06 on top, 14.03 on the bottom, and that gives us a scaling factor of 2. So that means the empirical formula was CH2. The molecular formula, you multiply those subscripts by 2, so it's C2H4. And that's how you calculate the molar mass of an unknown compound. Alright, that takes care of this lesson on empirical formulas. We'll practice these quite a bit. There'll definitely be some of these questions on the AP exam.